Okay, this little video is going to deal with curves to the left. So what we've got here is our normal adult hemoglobin curve for a human. Flat along the top, from sort of 14 to around about 11. Dropping, big steep drop, and then levelling off again down at the bottom, but always going down to 0. Now that is for human adults, but it is not for all organisms. So one of the issues about partial pressures is that it changes depending on your altitude. And I don't just mean going up a mountain, I mean going down into a burrow or going down into a deep lake. So we have a number of environments that have a lower partial pressure of oxygen in the environment. So probably altitude. So if you're going up a mountain, you're looking at things that live in burrows, and if you live in a burrow, the oxygen is diffusing into your burrow from the air. And of course, we can also think about fish because they have hemoglobin, and some of those can live in deep water where there isn't a lot of oxygen. So, if you haven't got a lot of oxygen in your environment, you then have an issue with getting oxygen. So say the oxygen in your environment is only at 8 kilopascals. The problem that you've got then is that you can't load up 100% of your oxygen. In fact, this line only goes to 91%. And that means that you can't carry, or you couldn't carry, enough oxygen round to your respiring tissues. So, instead of taking all the oxygen you can, you've got 10% less than normal going to your tissues. So, luckily, evolution is a wonderful thing. And animals that have evolved to live at altitude, so here I'm pretty much thinking, because I love the Emperor's New Groove, I'm pretty much thinking llamas. I'm sure there are others, yaks probably. If I'm thinking about burrows, I'm thinking about lugworm. And only because we're near Coniston and the other lakes. The deep lakes in the Lake District have a lovely, really tasty fish called char. It's like a cross between salmon and trout, absolutely gorgeous. Anyway, taste it if you get the opportunity. Llamas and lugworm are my two favourites though, because I'm thinking left, lower oxygen in the environment, llamas and lugworms, all the L's together. So, these organisms, and this is dead important, have a different hemoglobin. Different hemoglobin. It's still hemoglobin, it's still got 4 polypeptide chains, it's just slightly different. And this hemoglobin has a higher affinity for oxygen. Now that means that instead of fully loading only at, say, 11 kilopascals, it will fully load, it will take the oxygen even at 8 kilopascals. So, this hemoglobin gets fully saturated at lower partial pressures of oxygen. So if you're a llama living in the high Andes, your curve is pretty much going to be almost flat over to 8, and then it's going to drop down towards 0. So that curve is to the left. So and by to the left we mean to the left of the human adult haemoglobin. And I'm saying adult haemoglobin because our fetuses have a different sort of haemoglobin. So this is great. That means that they can load up there, they carry as much oxygen as possible, even if what they're breathing in has a much lower partial pressure of oxygen. So they're fully saturated at that lower partial pressure of oxygen that is available in the environment. So I did say that it was about adult haemoglobin, but also in humans, fetuses have their own particular haemoglobin. So I might do fetuses in a different colour. Green. So fetal haemoglobin. So again, different sort from adult haemoglobin. Has a higher affinity for oxygen. And the reason for that, if you think about this sort of curve, so its curve is to the left. If you think about that, where the fetus is getting its oxygen from is from its mother, and her oxygen by the time it gets to the placenta may not be, she's going to be using some of her own. If the curves were the same, then the fetus wouldn't be able to take, any oxygen away from its mother. But at any partial pressure of oxygen, the fetus can, because its curve is always above the adult one, because it's on the left, they're going to be able to remove that oxygen from the mother's blood. So fetal haemoglobin able to absorb oxygen from mother's blood. So that's it. It has to be at that higher affinity, and that therefore higher above that curve, which then puts it to the left. So there's one more curve that occasionally, well, enough that I'm going to mention it, gets asked about, and this is, I'm not sure about orange, so I'll use green if I find one. Or it'll have to be blue. So the other one is a curve that does, that's a bit of a wobbly line, that does this. Now again, this is a completely different pigment. It's not even haemoglobin. We don't even call it haemoglobin. It's called myoglobin. Myo means muscle. So this is a pigment in muscle cells. It's quite often crops up as contextual things, because you should be able to work it out from the fact that it is so far over to the left and that it's completely flat over to here. But I'm going to tell you anyway. It carries 1 molecule of oxygen as opposed to 4. And it will only unload, this is the key, it only unloads at very low partial pressures of oxygen. Now where do you get those very low partial pressures of oxygen? Here we're talking rapidly respiring tissues. That's where you'd find them in the body. They're using up lots and lots of oxygen, producing lots of carbon dioxide. So if we look at the curve for myoglobin, straight across and then almost straight down, so it's kind of dumping its one molecule of oxygen all at once into those tissues that have very low partial pressures, so it's unloading an oxygen. That's why the curve's so steep, it's only got one to give away. So only unloads at very low partial pressures of oxygen, and therefore we refer to it as, it's sort of acting as an oxygen store. So it's in these very rapidly respiring tissues, not only have you almost run out of oxygen from your hemoglobin, and then it's got a bit extra, that just sort of delays the onset of anaerobic respiration. And as I said the words at once, I thought, oh good Lord. Can you remember that this steepness of the curve does not refer to speed? There is no time on this. It just depends on what the partial pressure of oxygen is that is closest to those red blood cells. Nothing to do with speed. So it's not unloading faster, it's unloading more at that particular partial pressure. Okay, so that's our curves to the left. Super duper.